الآن يمكنكم المشاركة في مبادرة الأيام الرقمية تحت شعار انطلق بقوة مع جوجل، والتي يتناول فيها خبراء جوجل عناوين جديدة أسبوعيا مثل السحابيات، مهارات من جوجل، أندرويد، فلتر، ذكاء الآلة، فايربيس، ديزاين ثينكينج، مقسمة إلى دورات وورشات عمل يومية بالإضافة إلى مسابقات أسبوعية. شاهد الأيام الرقمية مباشرة على اليوتيوب وشارك رأيك وأسئلتك مع خبراء جوجل، واحصل على شهادة حضور في كل محاضرة تشترك فيها. هذا وأكثر من الأحد إلى الخميس ابتداء من الساعة 9 بتوقيت دبي عبر الرابط المبين youtube.com/gdgmena.
Hello everyone. السلام عليكم. صحة فطوركم وبشركم مبروك عليكم. مرحبا بكم في another session from the GDSC week. Thank you everyone for attending this session, and thank you GDG MENA for having us for another session. And hopefully by the end of the session you will learn something new. So and during this presentation I will talk about the brain tumor classification with TensorFlow, where I will discuss with you and explain the general process I follow for nearly most of the computer vision problems that I deal with. I will be with you. I'm Taha Bouhsine, the GDSC lead of University from Morocco. You can find me in the social media tags here on Twitter with Taha BSN, or on Kaggle and GitHub with SkyWolfMo, and also you can find me on my website. So by the end of this presentation, or what will you take with you by the end of this presentation, as you will learn the basic process and steps you need to take for if you want to create a machine learning solution for computer vision problems. Also, you will understand how you can explore your images before feeding them to the network. You will learn about how to use data augmentation to help your model generalize better and not overfit the data set. Also, you will learn how to evaluate your model and with different metrics and tools also. And at the end, you will get to discover the GradCam or the attention map to help you investigate where did your model false predicted things and why did your model false predicted things. So inshallah, during this session, we'll try to follow this plan. The first point, or the first part, we will talk about the disease, what is brain tumor. Then we will move to a small EDA on the data set of the brain tumor classification MRI data set available on Kaggle. And then we will move to the notebook that we will share with you later this talk, to see the modeling phase and the evaluation phase of our problem, of our solution. Then we'll get back to this presentation to discuss a conclusion and see if you have any questions or you have you want to discuss some things. So just a small disclaimer. I'm by no means a doctor or a medicine practitioner. I'm just a deep learning engineer trying to create a solution that will help in the screening of patients and improve the quality of healthcare using machine learning. So what is brain tumor? Most of the statistics that are used in this presentation are extracted from the American Brain Tumor Association and or the Center of Brain Tumor Registry of USA. That says that more than 88,000 people or patients are diagnosed each year. These statistics are 2022, and more than 4,000 of them are children below the age of 19. And also, the main or the most common cancer among the children below the age of 14 is the brain cancer or brain or central nervous system tumors. More than 700,000 people in the USA are living with a primary brain or a central nervous system tumor to this day. And by the end of this year, sadly, more than 70,000 of them will lose their battle against brain tumor. And what makes things more complicated is that there exists more than 100 types of brain tumor, which makes it really difficult to create a general solution, but we will try. So what is brain tumor? Brain tumor, it is a collection of abnormal cells that grows in the brain or the central spinal canal. It multiplies by just one abnormal cell becomes two, then the two abnormal cells become four, and so on and so forth, until there is a lump or a tumor of abnormal cancers. The other terms that are used to describe this disease is the tumor or the neoplasm, the lesion, space occupying mass, and many other terms that you will find if you read the literature about this disease. You will find them using generally these terms. So how do tumors form? Till this day, research is still trying to determine how does this tumor start, or how does this tumor form? Is it a cell-to-cell communication? Is it a compromised immune system? Or many questions they are trying to answer, but still are research in progress. And the most common symptoms of brain tumor, depending on what part of the brain got affected, we can find that a patient might have unusual headaches or seizures during the day, memory loss, personality or behavior change, and the inability to process incoming information correctly. And also, if the vision part of the brain is affected, the patient might face a blurred visions or double vision or change in the motor control, where he just tried to lose everything that he touches. And as we said, depending on what part of the brain got affected, the behavior of the patient change, and the symptoms correspond to the tumor location and size and type of the tumor. So how brain tumors are diagnosed? Generally, they tend to use the MRI images that are more that give more detailed images and more detailed description of the brain than the CT scan. But generally, during the CT scan generally use the X-ray, and MRI generally use the magnetic fields. But the CT scan is less expensive, so what they tend to do during emergencies, they use the CT scan first to get an initial image. Then later they try to use the MRI image to have more in-depth details on the case of that patient, and to confirm whether our patient have cancer or not. They generally use tissue samples that extracted from the brain, which is the most reliable method to diagnose a patient. And also, they might find some biomarkers that in tissues or bodily fluids that are being used to confirm the diagnosis. So for the primary tumor, it generally begins in the brain and tend to stay in the brain. And as we said, there are a lot of cases around the world. And it tends to be, there are two types of this primary brain tumors or brain tumors. The first one, which is the benign, which is not cancerous, or the malignant, which is a cancerous. And there might be some a tumor that have both of those cells. Also, there is the metastatic brain tumor, that is a cancer that starts elsewhere in the body, then spread to the brain. And it is always malignant, or it is always cancerous. So as we said, the question is it cancer or not? So for the benign tumors, they tend to grow slowly and do not spread that fast. But for the malignant tumors, they tend to grow rapidly and invade and destroy the nearby normal tissues and spread through the body, which is quite dangerous. And the World Health Organization, defined this international grade system to classify these tumors depending on the danger of them. The first grade, which is the least malignant and have a slow growth rate. Then the second part, which is a slow growing rate but can spread and can somehow recurrence or duplication or multiply. And then the third grade, which is the fastest, have a faster growing rate, and it's always malignant. and has quite often recurrence. Then the most dangerous one, which is the grade 4 tumor, that is the fastest and the most aggressive, and it's the most dangerous of them all. So the most common types of primary brain tumors. The first one is the meningioma. We will see some examples, some images about of each of these examples. There is also the gliomas that has 4 categories, which is the low grade astrocytoma and the malignant astrocytoma, or the glioblastoma, and also the oligodendroglioma. And then we can find the pituitary cancer, or the pituitary pilocytic astrocytoma. That is the most common in children. For the meningioma tumor, it is the most common type of primary tumors that arise from the menins, and which is the lining of the brain, and spread elsewhere in the brain. Then there is malignant glioma, which is a gliomas that arise from glial parts of the brain, and there are different types of gliomas as we discussed earlier. And then there is the anaplastic astrocytoma, which is a higher grade tumor that is quite dangerous. And then there is the glioblastoma, which is quite dangerous also. And we will see in the notebook, we will try to see each of those examples in more details. So how are brain tumor treated? Generally, they are treated using surgery to remove the tumor bulk if the case is not that dangerous. And also, they tend to use radiation to disable reproduction and shrink the tumor. And lastly, they use the chemotherapy to either kill the tumor cells or interfere with their growth. So let's get a bit practical. Okay, do you have any questions so far? Okay, if you have no questions, I think we will move into more practical things now. So we will try to look at the data set that we will be using, which is the brain tumor classification MRI available on Kaggle. And we will do a small EDA before moving to the notebook. So this data sets have about 4,000 images that are split into 4 categories. But the problem that we have here is that this data set is not. Wait, I will just laser pointer. This data set is not evenly split, as we can see that the no tumor class has just 400 samples, but the R class have 800 samples each. So it's not a balanced data set that then we should use, which lead us to use a weight balancing method, or just using data augmentation to help with this problem. And for the data sets, it has about 400 images, which are classified also into 4 categories. For the glioma, each of those classes, as we saw earlier, the glioma tumor, which is this part of which affected this part of the brain. There's also the meningioma tumor, which is this part, and there are the class that has no tumor, which is this part. Then there is the pituitary tumor that affects this place here. We will see more into code. Okay, so for this part, we will discuss a bit about the model architecture that we will be using. So I will use the model, the NASNet mobile model, which is from the family of NASNet. That generally contains 2 types of cells. The first type of cell, which is the normal cell that try to extract data, then the reduction cell. Okay, so I will move to the notebook right now. Just a minute. Start sharing this. Okay, I think you can see the screen here. Okay, here's this. Okay, you can see. Can you see? Yeah, you can see the screen. So in this notebook, I will be explaining. It's the same notebook, the same goals as the presentation goals. The first point, which is the general information about the dataset, which is just what we just discussed in this talk. I will be adding the slides later to this notebook. The first part, which is the imports and helper functions, the functions that we will be using later in this notebook. First of all, I try to install TensorFlow add-ons that contain some quite useful tools and that I will be using in the modeling phase. I've imported TensorFlow and Keras, and also the image data generator that will be that I need to for data augmentation, and Matplotlib for some data visualization, and also NumPy and Pandas, and Seaboard to make the visualization more better. And then the scikit-learn metrics, which is quite useful to evaluate our model. I've set the seed, the random seed to 548, and I've used a batch size of 64. And I've trained the model for about 250 epochs, and with a learning rate of 0.0005, and the image size of 224. And this is just the data path where the data set is on this kernel. Here I set the random seed of the TensorFlow. Why should we set the random seed for as amount of this notebook? It's to make sure that our model or our experiment is reproducible. It's not based on randomness, but it's based on really the model that it learned something, not just the model was better because we found a better seed that has affected his randomness. I will use this function to plot the history and accuracy, the accuracy and loss of the model. I pass to it the history of the model. Then I try to extract the accuracy and validation loss. Then I've plotted the data, the history of that model. Also, I've tried to plot the precision and recalls. We will see the implementation or the call of these models later. And then this is a print of the confusion matrix, where we can build a confusion matrix out of the prediction of the model, where after evaluation. Then this is a function that try to generate GradCam and the heat map of the GradCam, also the attention map, and then a function that extracts the false negatives out of the data sets, and a function to save the plots or to plot the image and its GradCam and the attention map. And I try to set the colors that I will be using for our plot to be a bit Googlish brand name. Then here I try to define the generators that I will be using to load the data set. The first one, which is just EDA data generation. It doesn't have any data augmentation. It just have a rescaling of the data set to make sure that it is normalized between 0 and 1. And here I've loaded the images from the training path, the training images to the EDA. Just take a look at it. There are about 870 images belonging to 4 classes. And then this is the data generator that we will be using to load the data sets for training. We split the data sets into 20% of validation sets and 80% of training sets. Rescale again to make sure that the images are normalized between 0 and 1. And we used a zoom range for zooming to the image. Just methods of data augmentation. Also a rotation range to apply random rotation to the image as it was loading, and a horizontal flip to make sure a flip here or a vertical flip or a horizontal flip, and the fill mode to make sure that we don't have transparent images when we did these augmentation. And for the test generation, we should not apply on any data augmentation, only the same rescale that we use for the training set. Here we loaded the images to to the training generator that we'll be using to train for the training set, and the validation, which is the validation data. Then the training generator, test generator, which is the test data. And we try to extract the number of samples, the training set or the validation set and test set, because we will need them when we try to when we will fit the model layer. And for the most important part for us, because we, as we said earlier, that we have an imbalanced data, then we should have a mean to weight balance. For weight balancing, what we will be using is the class weights, which is a variable available on the model.fit, which will feed it how much data, how much should we consider the class in the loss function. The second class, which was the no tumor class, which is the one with the least images, is augmented to about twice the amount the impact on the loss, which is quite impactful for various reasons. So let's explore our data. Sorry. So let's explore our data. I try to just here from the EDA, just to plot some images from the EDA generator, about 9 images. The first image belongs to the pituitary tumor, and the second image belongs to the pituitary tumor, that where where this part of the brain is what got affected, and same goes here. Then there is the glioma tumor, which is this part that got affected here, I think. And then there is also the meningioma tumor, which is quite visual. That here it's you can see it here, and there are other images. We will try to look for each class and what does it mean. So for the pituitary tumor, we can see that this place is what got affected, and if we look at it, I think this image is more visible. Pituitary tumor is more visible here. You can see that this part is what got affected, where the pituitary is quite big of its size, which identify the pituitary tumor. The same thing goes for here. And then the gliomas tumor, which is this part of the brain that got affected, and the meningioma tumor, which is this part of the brain, and the no tumor, which shows that this brain doesn't have any tumor at all. Well, there might be some problems in the data set, like this image should not be considered, as it might lead the model to misclassify this image. But things to improve and things to consider later. So as we said, for the transfer learning model, I've used the NASNet mobile. I try to initialize it with the ImageNet, the ImageNet weights, and with the image size of 224 by 124 by 3, and we froze the model. We froze this part of the model, so not to make it trainable, and we just keep the classifier, also only the classifier trainable. The first layer, which is the flattened layer, that turns the model, the 3D matrix, into a one-dimensional matrix, one-dimensional vector. It flattened the vector of the output of the transfer model. Then a dropout to help our model generalize better, and a dense layer of 16 neurons with the activation of ReLU, then dense layer, dense, and finally a dense layer of 4 classes. The number of classes we have is 4, and with the activation of softmax, because we used the generator used a one-hot encoding method to encode each of those classes, and a kernel regularizer. We used the L1 and L2 regularizer to help with the regularization of our model, the loss function of our model. And then we created the model out of the inputs of the transfer model and the output of this model here. I used the Adam optimizer with the learning rate of 0.00005, and I tried to use the metrics accuracy and precision recall and F1 score. Why should we use the order matrix? We will discuss it in the conclusion of this talk. Why the accuracy is not sufficient to accurately measure the performance of the model. Then I've tried to I've used the categorical loss cross entropy with the optimizer and metrics that we just defined, and the checkpoints to save the best model that we saw in all the epochs here. So for the model summary, I've tried to hide it here. It has a lot of text. We'll try to go down all the way here. Okay, it has about 5 million parameters and about 800,000 trainable parameters and 4,200,000 non-trainable parameters. Here we use the training generator for the training set, as a training set, and the callbacks to is the model checkpoint. Then the steps per epoch, which defines how many steps is the model gonna make before going into the next epoch. It was calculated here, I think. Yeah, it was calculated. Okay, I will try to hide this first. Okay. It was calculated where? Yes, it was calculated here. Here, yeah, which is the number of training samples divided by the batch size, and okay. Then we try to fit the model. I guess this is the verbose of the model. So we will not show it here, just hidden. I will share with you the notebook later. Wait just a minute to see it for yourself. And for the evaluation, these are the metrics. Just a recap on the metrics that we used. The false negatives, which are the false, where the model did predict falsely accused the model, and the true negatives. Then there is the true positive, which is where model accurately predicted the label, and where it didn't accurately predict that label, or where it predicted. The precision is the true positives on the sum of the true positive plus the false positive, and the recall is the true positives on the sum of the true positives plus the false negatives. Here are the formula here, but for the F1 score, which it is the 2 times the precision times recall, divided by the precision plus recall again. Each of those metrics are quite useful for various reasons. The accuracy, as we said, is not sufficient to see the model if the model is doing great for our case, for the medical case. Generally, we use the precision recall and F1 score to accurately evaluate the performance of the model. For plotting the accuracy and loss history of our model, we can see that the training samples try to stabilize on 0.9, on about 0.9 of the accuracy, and the validation accuracy, which is on the one drawn with red, stabilize on about 0.7 or 0.75 75% or 75% accuracy, which is not good. It's not that we can improve it later if we want to. And the loss functions keeps on diminishing, but on the training set, but for the validation set it was stabilized on about 0.5 0.7 loss. Then the precision, it was the same time. It stabilized around 13 epoch and didn't improve on the validation set. So it's time for the test evaluation. First of all, we will try to load the best model that had the best validation accuracy using the load weights method. We use the checkpoint to save the best models, the validation accuracy models, and then we will try to evaluate this model on the test generator. We got about 0.7 or 70% or 69% of the accuracy, and about 70%, as we said, it's not that good. So we have to improve on it, and we'll see how to improve on it later in the conclusion. And if we look carefully at this confusion matrix, we can see that the model made a lot of false negatives on the glioma tumor. It was misclassified as meningioma tumor here. About 12% of the dataset was misclassified as glioma tumor, and also the no tumor was misclassified as meningioma tumor, and also pituitary tumor was misclassified as meningioma tumor, and which has the most negative rate, the most false negatives in the whole dataset, which affected the evaluation of the metric and the accuracy of the model. And to investigate this more and to look for where did this model made false predictions, we will use the evaluate model function that we defined earlier to extract the false predictions out of the data sets, out of the test set. We have about 121 false prediction, and we defined the last layer of the model, of the transfer model of the NASNet model, that we will be using for the GradCam to extract the feature map, to extract what was the model looking at when he was making that prediction. The first image, the first case we have here is this one, which was the true label of it was the glioma tumor, and it was predicted as the meningioma tumor. Meningioma tumor with a high confidence of about 73%, 73% of confidence that this image belongs to the meningioma tumor. As you can see here, the part of the most yellow was the model was focusing on this part, and which made him to misclassify this tumor. And also this image, which is also the glioma tumor, and it was false predicted as meningioma tumor also. And we can see that he was looking at the right place, but he was classifying it as a glioma tumor, which is not right. But for this case, we can see that the true label was glioma tumor, and it was misclassified as meningioma tumor. But the model was not looking at the right place, was not looking at this place here, but it was looking elsewhere, was looking here. So it's something about the data set that made this model false predicted this thing. It's not about the model, but it's about the quality of this data set. So things to consider is to delete this part, or to make a mask of around this part where there is no brain, and to keep only the brain parts of this image, of all the images we saw earlier. And it was the same thing for this case, as we can see here. It's actually the same image, I think, but it's with a different angle, I think. And it was also focusing on this part, which is not good thing. And for this part, this image, it was the true label of it was glioma tumor, and what was misclassified as the meningioma tumor. And he was again looking at the right place, but not. He didn't classify it with a confidence of 95%, which is quite high, really, really quite high. He was 100% sure about it, but sadly he didn't make the right decision. And we'll look into other labels here, like just a minute. We will go to. As we said, the glioma tumor was one of the that have the most the highest about 42 misclassification. So for this case, the true label of this image was the meningioma tumor. It was misclassified as glioma tumor with a confidence of 80%. The model was not looking at the right place. It was looking here, I think. Yeah, he was looking here instead of looking at this place. And he was also looking at this place, which is not good. So it was not classified well. I think this part is what's made the model misjudge this image, focusing on this part, I mean, this part of the head. We should also, the same conclusion that we have, we should try to create a mask around the brain and only keep the brain for the classification. I think the same part of here, the tumor was here, but the model was focusing on this part. Okay. Okay. Do you have any questions? Okay, you have no questions so far. No, so for this one, it was misclassified as pituitary tumor, but the model was focusing on the wrong parts again. So it's not. We should also the same thing. We should also do a mask around the brain, around the unwanted parts of the head. And for this case, the brain tumor was classified in this part, which is weird. And then I will look at a no tumor, a no tumor example. The image, the model was focusing on this part of the brain, which is quite logical because there are some tumors that are quite dark. So the model was trying to classify this part of the brain. Also, this part of the brain, the darkest part of the brain. So we should really try to use some filters, for some pre-processing filters before feeding this image to the network to enhance these images. And also we can see that the model was not focusing on the right parts. It was focusing right here instead of focusing on the parts of the brain where the brain is not active again. And so on and so forth. For the pituitary tumor, it was misclassified as no tumor. For the pituitary tumor, it's quite normal around the brain, but only this part of the brain is big. So it's quite logical that the model was misclassifying those things. Here, he was trying to focus on these parts of the brain. And also here, he was trying to focus on this part of the brain, which led him to misclassifying as meningioma tumor. And so, what should we do to deal with this for these images? I think it's enough. It's enough dealing with these images. The important conclusion that we have. So what metrics is quite important for our case? Accuracy is not sufficient, as we said, as we said earlier, to measure the performance of a model that is intended for the medical use cases. Looking at the F1 score and recall is quite helpful. Also, the precision. How to improve on the results of this data set? I think one thing we should consider if we want to improve the results is, as we said, creates masks around the unwanted parts of the brain and only keep the brain, only keep the image of the brain instead of the skull or everything else. Train models with more epochs to see if to see all the image or the augmented data examples, as we when we are using the image data generator. Generally, it doesn't augment the data set, but it just apply when you are loading the images to the model after for each epoch. It tries to apply a random transformation to the image to make it different from the images previously, the model previously saw. And also, we can use the cross-validation. And finally, we can use the Keras tuner to tune the model hyperparameters and to look for better classifier to help us classify this data set. Okay, let's go back to the presentation slides. Oh, as we said, for the evaluation, we had some conclusion. So, notes to take out of this presentation, as these solutions that are created with machine learning for medical uses, for medical users, they tend to help in the screening of patients earlier and improve the quality of health systems and healthcare systems. Also, they increase the efficiency of doctors and availability of them, and also replace the expensive cost of creating domain experts, where we have to teach doctor 12 years, about 17 years to just be an expert in brain tumor and cancer in general, and hopefully save more people with these solutions. But one thing for sure, we should not trust our model 100%. We should use it to screen first, then confirm the diagnosis later with other means, as like the biomarkers or anything else. I will share with you the presentation. We will share with you the presentation. It has some references that I used to create these slides and present and notebook. Feel free to check them out anytime, sir. Thank you very much, everyone, for attending. If you have any questions, feel free to ask. Do you have any questions? Feel free to ask. I have no questions so far. Thank you very much, everyone, for attending the sessions. صحة فطوركم وصحة سحوركم. And I think see you in the next one, inshallah. Bye bye.